3.1 Intermolecular and Interparticle Forces. Topic overview. Intermolecular forces, or IMF, are the attractions between atoms, ions, or molecules that hold them together. There are 6 different types of IMF. They differ in the arrangement of the electrons. Intermolecular forces explain why carbon dioxide, CO2, is a gas, water, H2O, is a liquid, and silicon dioxide, SiO2, is a solid, even though they are all only made from 3 atoms. To determine which type of IMF a substance will exhibit, you need to look at the types of atoms that are present in the sample. Start by identifying the types of atoms in the sample as either a metal or a nonmetal. Remember, metals are to the left of the stair-step line on your periodic table, and nonmetals are to the right. The chart below shows a summary of the IMF and their strengths. London dispersion forces, LDF. All substances have LDF. This is the only force in nonpolar molecules or single nonmetals. Dipole-induced dipole. Polar molecules inducing a temporary dipole on a nonpolar molecule. Dipole-dipole. Polar molecules or asymmetrical molecules with only nonmetals. Hydrogen bonding. Occurs in polar molecules that have hydrogen directly bonded to N, O, or F. Ionic. Metals with nonmetals. Metallic. Only metal atoms. Covalent network. Bonding between carbon and either silicon, oxygen, or another carbon. Can also occur when silicon is bonded to oxygen. London dispersion forces, LDF, and dipole-induced dipole interactions. London dispersion forces occur in all substances. The force is caused by the movement of electrons within an atom or molecule. As the electrons move around the atom or molecule, there is a chance that they are unequally distributed. When this happens, it causes the atom or molecule to have a temporary dipole due to the partial negative charge, delta minus, in one section of the molecule. As a result, there is an area that is deficient in electrons that has a partial positive charge, delta plus. The temporary dipole in one atom or molecule causes the neighboring atoms/molecules to change. The negative end of the temporary dipole repels electrons while the positive end of the dipole attracts electrons. When the neighboring species electrons move, this forms an induced dipole which is electrostatically attracted to the first atom/molecule. This is usually a short-lived occurrence and will return to being evenly distributed, which is why LDF and dipole-induced dipole interactions are weak forces. Polarizability. One very important concept in this topic is the ideal of polarizability, which is just the ability of an atom or molecule to form a temporary or induced dipole. Polarizability is stronger when an atom or molecule has more electrons available to polarize. On the periodic table, the state of the halogens, group 17, changes from gas, F2 and Cl2, to liquid, Br2, to solid, I2, at room temperature. The molecule with the most electrons, I2, has a greater polarizability, and as a result greater LDF and a higher boiling point. Large molecules have stronger LDF because the increase in number of electrons increases their polarizability. Another factor that increases the strength of the LDF is the shape of the molecule. Long, thin molecules have more surface area and are more polarizable, while short, round molecules have less surface area and are less polarizable. More exposed atoms means more polarizability. If everything else is equal, polarizability is also enhanced by pi bonding, which is the presence of double or triple bonds. The more polarizable the molecule, the stronger the LDF will be. Dipole-dipole interactions. Dipole-dipole interactions occur between polar molecules that have permanent dipoles. Remember, molecules are polar when their electron distribution is asymmetrical. A Lewis structure can show if a molecule's electron distribution is symmetrical or not. Dipole-dipole interactions are similar to LDF, except that the dipoles are permanent and the attractions are generally greater. The partially positive end of one molecule is attracted to the partially negative end of a different molecule, and so on throughout the system. Dipoles can be measured by the dipole moment of the molecule. Dipole-dipole interactions are stronger when the substance involved is more polar, meaning that their electrons are more unequally distributed. Be sure to consider the electronegativity values of the elements involved. Hydrogen bonding. This force has a confusing name, because it is not a bond in the sense you may be used to. It is not a covalent or ionic bond between atoms in the same molecule, but instead an intermolecular force between two molecules involving hydrogen. Hydrogen bonding occurs in molecules that contain HN, HO, or HF bonds. The difference in electronegativity between these two atoms is so large, the temporary dipole that is made forms very strong attractions with other molecules. The hydrogen forms a partial positive charge, delta plus, and the N, O, or F carries a partial negative charge, delta minus. The positive hydrogen end can be attracted to a different partially negative atom on another molecule, and the negative N, O, or F end can be attracted to a different partially positive atom on another molecule. The picture at the right shows a hydrogen bond between molecules of ethanol. Summary of IMF. The following table shows the type of IMF present between two different substances. Notice how every one of these interactions lists London dispersion forces as present. If substance A and substance B are both nonpolar, only LDF are present. If substance A and substance B are both polar, LDF and dipole-dipole interactions are present. If substance A is nonpolar and substance B is polar, LDF and dipole-induced dipole interactions are present. If substance A is nonpolar and substance B is an ion, LDF and ion-induced dipole interactions are present. If substance A is polar and substance B is an ion, LDF and ion-dipole interactions are present. If substance A and substance B both have hydrogen bonding capability, LDF, dipole-dipole, and hydrogen bonding are all present. Not technically IMF. Ionic bonds, metallic bonds, and covalent networks are not technically IMF, however they are often mentioned when talking about the IMF outlined above. Due to Coulomb's law, ionic bonds are stronger when the charges of the ions are larger, and the ions are smaller. This was discussed in detail in topic 2.3. Metallic bonds can be pure metals or alloys of metals and other elements. This was discussed in detail in topic 2.4. Covalent network bonds form when multiple covalent bonds form a large macromolecule. These 5 covalent network molecules should be memorized: carbon and graphite, carbon and diamond, carbon-6, silicon dioxide, silicon carbide. Effects of IMF. The following effects of increasing IMF are shown in various compounds and will be discussed in more detail later in the course. Boiling, melting, and freezing points increase with increased IMF. Enthalpy of fusion or vaporization increases with increased IMF. Vapor pressure decreases with increased IMF. Viscosity increases with increased IMF. Surface tension increases with increased IMF. Solubility decreases with increased IMF. Lattice energy increases with increased IMF.